In this section, we're going to look at natural exponential functions. This goes with section 4.2 in your text. We'll start out with the limit definition of e. You can see it's an irrational number. It's defined to be the limit of 1 plus x to the power of 1 over x as x is approaching 0. Notice that e to the x is positive for all values of x. And if we took a look at the graph, the x-axis would be a horizontal asymptote on the left side. And also notice that because of that being the horizontal asymptote, that means that the limit as e to the x approaches negative infinity is going to be 0. For example 1, we're supposed to complete the table of given values for the function g of x is equal to e to the negative x, and then we're going to sketch the graph of g. Okay, so what we're going to do is we want to take negative 2, and we would like to plug it in for x into the g function. And then we would like to take negative 1 and plug it into the g function, and then 0, and also positive 1 and positive 2. And so what I'm going to do is I'm going to plug these into my calculator and see what values I get. Okay, so here I now have my chart filled in. We took e, which was my function, and raised it to the opposite of negative 2, which gave me 7.389. And then e we raised to the opposite of negative 1, which gave me 2.718. And so on down here. Now all I need to do is graph these things. Alright, so we know we're going to go backwards. I'm just going to draw my x-axis right here. And my y-axis, nope, not there, right here. Maybe not. Negative 1, negative 2, negative 3. Over here we have positive 1, positive 2, positive 3. Alright, so at negative 2, the graph is going to go up above 7. So it's between 7 and 8. So we got 1, 2, 3, 4, 5, 6, 7. So somewhere up in this area. At negative 1, we're going to be between 2 and 3. So here's 2, here's 3, here's 2.5. We're going to go a little bit further than that. At 0, we're going to be right here at 1. At 1, we're going to be at 0.36, so that's a little bit less than a half, so we'll be down in here. And then at 2, we're going to be at 0.13, so that's going to be even further down here. And so it looks like this side of our graph is going to come down here and ride right alongside the x-axis, and this side over here is going to be growing incredibly quickly. Now, in case you're wondering, we're talking about how the x-axis was supposed to be a horizontal asymptote on the left. We can see that's not true here. That is because the exponent was negative. This was e to the positive x, then it would be going in this direction, and we would have our horizontal asymptote back here on the left. Your book introduces something called a logistical model, which is still kind of like the exponential growth, but the difference between them, you can see with their exponential, we've got infinite growth going on right here, and even though we seem to have infinite growth going on right here, there actually is another horizontal asymptote up here at the top, and so this guy eventually is going to start increasing at a decreasing rate. In other words, it's still going to be increasing, but the amount that it's increasing is going to be less and less and less, and it starts right here at this point of maximum growth. Okay, alright, so we use the logistical model when growth is restricted. Here's what our model looks like right here. We've got f of t equal to a divided by 1 plus b times e to the negative kt power, and then this particular graph is called a logistic curve. Alright, so let's take a look at example 2. We have a bacterial culture growing according to the model y is equal to 1.5 divided by 1 plus 0.2 times e to the negative 0.5 t power, where t is greater than or equal to 0, y is the culture weight in grams, and t is the time in hours. And we want to find the weight of the culture after 0 hours, 1 hour, and 10 hours. And then we want to find out what the limit is of the model as t increases without bound. In other words, as t goes to infinity. Okay, so the first part of this is just going to be a plug and chug. We want to figure out what y is equal to when t is equal to 0, what y is equal to when t is equal to 1, and what y is equal to when t is equal to 10. So let's start there. Alright, when t is equal to 0, we'll have y equal to 1.5 divided by 1 plus 0.2 times e to the negative 0.5 times 0 power. Okay, the 1.5 is not going to change. Now, in the bottom here, 0.5 times 0 is just 0, and e to the 0 power is going to be 1. So we've got 1 plus 0.2 times 1, which means we're going to have 1.5 divided by 1.2. And let's see what that gives me in a calculator. It looks like it's going to give me 1.25 grams. Alright, let's do this again when t is equal to 1. That means we have y equal to 1.5 divided by 1 plus 0.2 times e to the negative 0.5 times 1 power. That means we've got 1.5 over 1 plus 0.2 e to the negative 0.5 power. And if we put that in the calculator, it looks like it's going to give me 1.338 grams. And finally, we want to do this when t is equal to 10. So we'll have y is equal to 1.5 over 1 plus 0.2 times e to the negative 0.5 times 10. This is going to be 1.5 divided by 1 plus 0.2 times e to the negative 5 power. And in the calculator, this is giving me 1.498. Okay, now for part 2, we're going to try and figure out what the limit is. Alright, so we are trying to find the limit of 1.50 divided by 1 plus 0.2 e to the negative 0.5 t as t approaches infinity. Alright, I'm going to rewrite this a little bit. I'm going to rewrite this as the limit as t approaches infinity of 1.50 divided by 1 plus 0.2 over e to the positive 0.5 t power. Alright, and the reason I'm going to do this is because I'm going to be able to take the limit of each of these individually now. So the limit of a constant 1.5, that's just going to be the constant 1.5. The limit of 1 is just going to be 1. Now, let's look at this fraction right here. As t gets larger and larger and larger, 0.5 times t is going to cause this denominator to also get larger. Okay, now, as your denominator in a fraction gets larger but the numerator doesn't change, that means the value of the numerator is getting smaller and smaller and smaller. So this piece of our function is actually approaching 0. And so our fraction becomes 1.5 divided by 1 plus 0, which is going to give me 1.5. And for future reference, that 1.5 came from right here in the numerator. That is not an accident. This is called the limiting quantity right here. And here's just a review of your compound interest. This particular formula is done without the years on it, so it's without time t. This is what everything stands for here, but as far as calculus is concerned, if we take a look at this formula, and as we increase in without bound, the amount A is going to approach a limit, and that limit is right here. It's P times e to the r. This should look familiar to you because that is where you get your continuous compounding formula, or the PERT formula I like to call it, which is P times e to the r times t power. And this is your compounded formula when you have like the number of times a year that it's actually compounded. So continuously we're going to use PERT. If we have quarterly, annually, monthly, daily, or whatever, we're going to use the first one here when it's compounded a particular number of times per year. Alright, so example 3 here, we want to find the balance in an account when $2,000 is deposited for 10 years at an annual interest rate of 9%, and we're going to compare the results and make a general statement about compounding. Okay, now quarterly means n is going to be equal to 4 because we're going to get interest compounded 4 times a year. Monthly means n is going to be equal to 12 because they're compounding interest 12 times a year. Daily, we're going to use 365. I know this year was a leap year, but we're going to use 365 because interest is compounded daily. And then continuously, well, for this one in particular, we're not going to have an n, but we do know we're going to have to use the PERT equation on that one because of the word continuously on there. Okay, all right, up here, $2,000 is deposited. That is our principal amount. For 10 years, that is our time. At an annual interest rate of 9%, that tells me that R is going to be 0.09 when I write it as a decimal. And let's see if we can figure these out. The amount in the account is going to be 2,000 times 1 plus 0.09 divided by 4 to the power 4 times 10. All right, let's see what this is going to give us. I'm getting $4,870 and 38 cents. And be sure you round this off to 2 decimal places because this is money. Alright, monthly. The amount in the account will be 2,000 times 1 plus 0.09 divided by 12 to the power 12 times 10. Let's see what this is going to give us. This is giving me $4,902.71. Alright, let's do daily. We'll have $2,000 times 1 plus 0.09 divided by 365 to the power of 365 times 10. Now we would think this would be a very large number because you're getting interest 365 times each year. So for 10 years, we're getting 3,650 times that interest is calculated on our money here. And this is giving me $4,918.66. So this is a little disappointing because just going from monthly to daily, our increase was only $16, or almost $16, and that was it. All right, let's see what continuous is going to do for me. The amount in the account is going to be the principal times e to the power of r times t. And this is giving me 4,919.21. Okay, so it did go up, and it went up not even $1 going from daily to continuously here. So what we're supposed to see is the fact that even though we're increasing the number of times that interest is calculated, and even though the amount of money that we have is increasing, it's not increasing as much the more times that we introduce calculating the interest in there. Okay, so this kind of goes back to something I said earlier, and that is the fact that the balance, or A, is increasing at a decreasing rate. As N increases. Okay, now we introduce something called the effective rate. Okay, the banks will give you your annual interest rate, your stated rate, which is also known as your nominal rate. If they say, hey, we're going to pay you 10% interest just for the privilege of keeping your money in our bank, that's not what they're actually paying you. They're paying you an effective rate. And where they're going to get you on this is when they talk to you about your credit cards. Okay, with the savings account, they'll tell you something like, oh, we're actually paying you 10.12%. Okay, and when, if you were to do it in the formula, you would probably do it with 10% instead of the 10.12. But you would find that over time, the amount of interest that you got is not actually 10% of what you put in there, because you've been earning interest on your interest. So you might have gotten 10.12% on your initial investment. But like I said, where they're going to get you is on the credit cards, because credit cards have these astronomical interest rates on them, like 25%, 29%, 20%, especially when you're first getting one of them. So when you look at that and you're like, oh man, this is such a large interest rate anyway, but then you take a look at the effective rate and you find out, oh, I'm not really paying 25%, I'm actually paying 25.23%. And 0.23 doesn't sound like a whole lot, but over time, because depending on how much you put on your credit card, it can really add up there. Okay, so what we're doing is we're going to take this part of the formula here, the 1 plus 1 over r to the n power, and subtract 1, and that'll tell you how much interest you're actually getting on your initial investment, or how much interest you're paying on your initial, borrowing. Okay? Alright, so here in example 4, we're going to find the effective rate of interest. The nominal rate is at 7%, so that tells me we're going to be using 0.07. And it's going to be compounded these 4 different ways. So annually means n is going to be equal to 1. Semi-annually means it's going to be equal to 2. Quarterly, we said a minute ago, was going to be equal to 4. And then monthly, we said, was going to be 12. Alright, so our effective interest rate is going to be 1 plus 0.07 over 1 to the first power minus 1. Now, all of this in here, this is going to be 1.07 and then minus 1, which is just going to give me 0.07. So this really shouldn't be a surprise, because if your initial investment is $100, and you're getting 7% interest, but you're only getting it one time a year, then your annual interest rate is going to be the same as your effective interest rate, because you're only getting interest once. So the effective interest rate really is only good for us when we are accruing interest more than one time a year. Okay, let's look at semi-annually. Alright, so the effective interest rate is going to be 1 plus 0.07 divided by 2 to the second power, and then minus 1. And I'm going to put this all in the calculator at one time, so we're going to have and this is giving me 0.712. So 0.712, which is about 7.12%. And this one was at 7%. So you can see just by increasing the number of times that we're getting interest by 1, we're already getting some extra interest in here that we wouldn't have gotten previously. Alright, let's look at quarterly. The effective interest rate, 1 plus 0.07. This time we're dividing by 4 and raising everything to the 4th power. And this is giving me 0.719, which is about 7.19% interest. So we've increased it a little bit more. Not quite as much this time, going from semi-annually to quarterly. And then let's do this for monthly. 1 plus 0.07 divided by 12 to the 12th power. And this is giving me 0.723 or 7.23%. So we've gone up even less going from quarterly to monthly, but again, it's still increasing, and that's because of those extra times that we're earning interest on the interest that we've already earned. Okay, so the last thing we want to look at here is present value. And what we're looking at with present value is sometimes you know how much money you want to have at a certain time. Like if you're trying to buy a car. So let's say you want to buy a car and your car costs $25,000, and you want to know how much money you need to put in the bank so that it will earn interest, because you're not going to add anything else to it. You just want to put some money into the bank. And let's say you've got 5 years you can wait for this car. Alright, and so you've got an interest rate, and what this present value is going to tell you is how much money you need to put in the bank right now so that you can have the balance that you want in the time frame that you want with the interest rate that you've been offered. As long as the interest rate doesn't change, it does need to be fixed. And so what happened was somebody took the compounded equation and just rearranged it and solved it for P, as you can see. And we do have two options. We got this one and we have this one. I personally like the top one better, just because if we use the bottom one, we're still going to have to figure all this stuff out down here, and it's just an extra step to do. Alright, so last example here. How much money should be deposited in an account paying 6% interest compounded monthly in order to have a balance of $20,000 after 3 years? Okay, 6% tells me my interest rate is 0.06. The balance is $20,000. This is A. This is the amount that I want to have in my account. And then the years here, this is my T. Okay, so using that top formula there, we need to know P, the principal. What do we have to have right now to invest? Alright, so P is going to equal the amount that we want, which is $20,000, divided by one plus the interest rate over 12. We forgot to do that part right there. This is n to the power 12 times 3. Okay. And again, this is going to be money, so be sure you round it to 2 decimal places. Alright, let's put this in the calculator. And this is giving me $16,712.90. So this is what you need to have in your pocket right now in order to open up an account at 6% interest that's paying you monthly, and you can save it for 3 years. You should have about $20,000 at the end.